Right. So that's going to be pretty much most of the math that we'll be doing. We'll be doing funner things now, like looking at code. So let's go over 4a of your worksheet. So we have this function right here. We want to be doing a code model of that. First of all, this first line in x equals 0 is doing just constant work. And then this loop right here operates n times. This loop right here operates n squared over 3 times. And this one is just doing constant work. So notice here that this entire loop, this inner loop, does n squared over 3 work in total, right? Because it's like n squared over 3 times constant work. But then it is nested within something that operates n times. So in total, this will operate n times n squared over 3 times. And then so our recurrence will be n to the power of 3 divided by 3. And there's probably some constant in there, but we're just dropping it. And so from this code model, we can get our big O bound, which is just dropping the constants 1 over 3. And so the worst case runtime of our function is going to be n to the power of 3. All right, now for 4b, so just straight up, we have constant work right here, but now we have this loop, right? So this loop, if we look at it at a glance, it seems that it'll always run n times, right? We start I at n, and we reduce I until I reach 0. But it turns out that this break statement actually does something special. It will break whenever I is divisible by 3. And I argue that this will always happen within 3 iterations. Because we're decrementing I only by 1, after either the first, the second, or the third iteration, this loop, this requirement will be satisfied and will break from this for loop. So yeah, at most this for can run 3 times. So in the worst case, we only do 3 times 4, right? Because there's 4 work over here, which is equal to 12. So we're only going to be doing 12 work in total within this for loop. So in total, our code model is essentially just doing 13 work. And surely enough, that's going to be a constant big O.